specific type of chemical reaction known as an equilibrium reaction. So here you have N moles of A reacting with O moles of B, and that's going to go create P moles of C and Q moles of D. A and B are your reactants, and C and D are your products. Now, usually these reactions go to completion, but an equilibrium reaction does not go to completion. So at the end of the hour, or at the end of the day, or at the end of the month, or at the end of the year, you let this reaction go, you're still going to get not only products C and D, but you'll also get some amount of A and B. So we designate equilibrium reactions by this back arrow, which means that during the reaction completion, we're still going to have leftover reactants A and B. So a reaction that's in equilibrium has what's known as an equilibrium constant, and the equilibrium constant is a number. It does not have any units, unlike rate constant, small k. The equilibrium constant does not have any units, but it's a number that relates to the concentrations of each of these at equilibrium, such that for every reaction that's going to proceed in the right-hand direction, there will be a back reaction that proceeds at the left-hand direction. So in essence, this reaction will settle at a certain amount of concentrations whose ratio is going to be the equilibrium constant. So the equilibrium constant is the law of mass action implies that this equilibrium is going to settle as stated before. You can also perturb this equilibrium. You can perturb the equilibrium and the reaction is going to offset. That is known as Le Chatelier's principle. Another important aspect about the equilibrium constant is that these concentrations are what's known as equilibrium concentration. So this is an important point. The concentration of A, as well as the concentration of B, as well as the concentration of C, as well as the concentration of D, are equilibrium concentrations. You want to contrast A, B, C, and D, which are non-equilibrium concentrations. And if they're non-equilibrium concentrations, then we have to do what's known as an ICE table. The initials in ICE table stand for initial, change, and your final equilibrium concentration. In other words, if you have A, B, C, and D as non-equilibrium concentrations, this reaction is going to settle, move a little bit to the left or move a little bit to the right. It's going to jiggle around until it establishes those equilibrium concentrations that satisfy this equation. So the equilibrium constant, just like the rate constant and vapor pressure, it has to be quoted at a specific temperature. So this equilibrium constant is quoted at either a temperature 25 degrees or 50 degrees or whatever the temperature this equilibrium reaction is going to be held. Final and most critical point about this equilibrium constant quoted at a specific temperature is that solids and liquids are omitted from the equilibrium expression. So if this state in either the products or the reactants is a solid, it does not get put in. And if the states in the products or the reactants is a liquid, it does not get put in. Now, there's a reasoning behind not putting or omitting solids and liquids in this equilibrium expression. Solids usually are not expressed in concentration units. There's no such thing as molarity of lead, which is a solid. There's no such thing as molarity of silver. Solids are usually measured in terms of density, so that's an accurate representation. It's an accurate quantity of a solid, not molarity, but density. So solids do not get put into the equilibrium expression. Liquids do not get put into the equilibrium expression because most of the reactions, if there is a liquid involved, that liquid is a solvent. And the solvent is the dissolving medium in which the reaction occurs. So aqueous solutions or aqueous reactions, the liquid there is water, and that is where the reaction is going to occur, in the dissolving medium. So the solvent does not participate in the reaction. The solvent is just the medium in which the reaction proceeds. Yes, it does have a concentration, but usually it's not participating in the reaction, or it's just so large that it has no bearing on the reactants and products, which are in a much smaller concentration than the solvent. So solids and liquids are omitted from the equilibrium expression. So this means aqueous solutions, the aqueous concentrations, are put in, and gases are put in as well. So all reactions that have an equilibrium, look for the back and forth arrow that expresses an equilibrium reaction, a reaction that does not go to 100% completion. And the equilibrium expression for this reaction is acetic acid reacting with water, giving you the acetate ion and hydromonium ion. So this is going to deal with the next chapter on acid-base chemistry, so we will not go into the details and dissect this reaction, but enough to say that we can get the equilibrium constant. It is the concentration of the products raised to their stoichiometric coefficient. So it's going to be the concentration of acetate, the concentration of the hydromonium ion, divided by the concentration of acetic acid. A lot of times we have the subscript designation. You may have seen the equilibrium value being mentioned like this, where EQ is a subscript. This C can also be a subscript. That would be a concentration, which means your equilibrium components are in terms of concentrations. You may also see Kp. That means your equilibrium terms in the expression are gases, so that's a pressure. We're also going to see something a little bit later on the course called Ksp. That's the solubility product constant, and that has to deal with solids that are in equilibrium with its component ions. So just be aware the subscript really is just a marker for us to tell us and gives us information on what type of reaction we're really dealing with, whether it's just equilibrium concentrations. You're just as fine putting a KEQ, but you can put C, which is designation for concentrations, P, which is a designation for products, or KSP, the solubility product constant, which is a designation of a solid that's in equilibrium with its component ions. For example, a KSP reaction, example of a KSP reaction would be the silver chlorides precipitate in equilibrium with silver ion and chloride ion. You know, the equilibrium constant is going to be products over reactants. We call this a KSP, and the product silver ion times the product chloride ion. So just a brief comparison of rate constant K versus equilibrium constant big K. First of all, these are both quoted at specific temperatures. We looked this up, particularly the equilibrium constant. So there's tables that will give you the equilibrium constant for a particular reaction at a particular temperature. If you go all the way up, the equilibrium constant for the dissociation of acetic acid to acetate and hydromonium ion is quoted at 25 degrees, and that value is 1.75 times 10 to the minus 5. So usually if we're not computing them at a specific temperature, we're calculating them by plugging it in to this equation, the equilibrium constant equation, which is the law of mass action. So the rate constant K is correspondent to the rate law. The equilibrium constant K is correspondent to an equilibrium concentrations where the concentrations settle. The small k is referring to rates, and this big K is referring to which way the reaction is going to proceed to get to that equilibrium constant at that temperature. The way you calculate these are a little bit different. This is the law of mass action. This is more the rate law. And the exponents. So the exponents here in the rate law, nothing more than zero order, first order, or second order. We have to calculate that based on our data table. Here, the exponents, nothing more than the coefficients of the balanced chemical equation. So it's critical that the equations remain balanced. The units differ for rate constant small k. It depends if it's zero order, second order, or first order decay of the reactant to the products. In the equilibrium constant, we have no designated units. There's something called the reaction quotient. The reaction quotient gives you information on where the reaction will shift in an equilibrium based upon its relationship to the equilibrium constant. So there's no application for the rate constant because this gives you no information on how fast the reaction is going to go. The reaction quotient gives you more information on whether the equilibrium will be offset more to the reactant side or the product side. So essentially you compare the reaction quotient to the equilibrium value, and that tells you where the reaction is going to go to establish equilibrium, either to the reactants or to the products. So our one problem here that involves working with the equilibrium expression, Write Kc and Kp for the decomposition of dinitrogen pentoxide. This will disassociate or disintegrate to nitrogen dioxide and oxygen gas. So remember the law of mass action, products over reactants. Each of them raised to the stoichiometric coefficient. So the C here stands for concentration. A gas can be measured in terms of concentration or it could be measured in terms of pressure. If we were to have a Kc here, let's put the concentration of the gases. So NO2 concentration, that's raised to the 4th power. The O2 concentration of the gas, that's raised to the power of 1. All of that divided by the concentration of N2O5, that is raised to the 2nd power. So that's pretty easy. We can also do the Kp if these guys are in pressure, so we can have, remember, these are gases, so we can have a pressure of NO2 raised to the power 4. We can have a pressure of oxygen, that's not raised to any power. And then we can have the pressure of N2O5, and that's raised to the 2nd power. Now we can actually interconvert between the equilibrium constant Kp to the equilibrium constant Kc based upon the gas law. So that derivation is the equilibrium constant for gases is equal to the equilibrium constant for those gases measured as a pressure, as a concentration, times RT, that is raised to the power of delta N. And that delta N is the change in the moles from products to reactants. So we can actually do that for this reaction here. So our Kp is nothing more than Kc times R, 0.808821 times T. We're not given a temperature here, but if we were given a temperature, we'd have to convert that to Kelvin, and all of that raised to delta N. So what is delta N here? What is delta N here? Well, it's the change in products in the number of moles. N is the number of moles. So we have 4 plus 1, 5 moles on the product side. We have 2 moles on the reactant side. 5 minus 2 is 3, so all of that raised to the 3rd power. The way you would compute this if you were given a temperature is you convert that temperature to Kelvin multiplied by the gas constant qubit, and then multiply your corresponding equilibrium concentrations, and that will give you Kp. It's very important to realize that these are equilibrium concentrations to discriminate against non-equilibrium concentrations. The reactions are going to settle. They're going to settle at a specific concentration of this reactant and a specific concentration of these 2 products, and that ratio, according to the law of mass action, is going to equal to Kc. It's the same thing with the pressures. So with gases, you have to deal either with the pressure situation or the concentration situation. This problem, you're given the equilibrium concentrations. So read the problem very carefully. Equilibrium concentrations. And it's between carbon monoxide and molecular chlorine to give you carbonyl chloride. So if these are equilibrium concentrations, and the rate constant is given at a specific temperature that you must calculate, and you know these are equilibrium concentrations, these are going to be the final concentrations when this thing settles, when this reaction settles. So all we have to do is just plug and chug, because once again, these are equilibrium concentrations. Divided by carbon monoxide is 1.2 times 10 to the minus 2, and my chlorine gas is 0.054 molar. Equilibrium constant does not have units, so I can just put that into my calculator and get an answer. I get a value of 216, just go 0.05, just maybe for my sake an extra 2 decimal places, so that's the equilibrium constant at 74 degrees C. Now, the magnitude of the equilibrium constant tells you which way the equilibrium is actually shifted. It's not that you're going to have 50-50 and it's not going to be even reactants and even products. The equilibrium will favor either products or reactants. So while in this particular reaction you will have at the end of the day or at the end of the year or at the end of the month or at the end of wherever, you're going to have some of this, and some of that left over, but this high equilibrium constant tells us that you're going to have more of the product side. So the equilibrium actually favors products, but you will have some remnant reactants whenever this reaction is finished. So looking at this problem here, we're having this equation. It's balanced, and the partial pressure of each gas is 0.265 atmospheres, and the reaction is being conducted at 395 temperature. Don't forget, this is quoted at a specific temperature, Kp and Kc. So anytime we have gases, that means that here we don't have a gas. Anytime we have gases, that means we either could have a Kp for the reaction or we can have a Kc for the reaction. So let's do both here according to our equation. So our equilibrium constant, let's look at pressure P, and that's going to equal to the pressure of NH3 times the pressure of H2S. Does not get included into your equilibrium constant. I've seen many mistakes where people put the solids in the equilibrium constant. That's not correct. So the pressure of NH3 is 0.265 atmospheres. The pressure of H2S is also 0.265 atmospheres. The equilibrium constant has no unit, so I don't have to worry about any of that. And the equilibrium constant for this reaction at 395 Kelvin, that's important, is 0.072. That's Kp. We can also go ahead and get a Kc for this. So our relationship between Kp and Kc is this. P is equal to Kc times, this is value of R is 0.0821 liters atmospheres mole Kelvin. Times K, the K for this reaction is 395 Kelvin. All of that raised to change in the number of moles. The change in the number of moles, well, we have 1 mole here and 1 mole here, 2. We don't even consider the solid portion, so 2 minus 0, products minus reaction is squared, so that's 2. We have our value of Kp as 0.0702, so I'll just plug everything in and solve for Kc. Solving for Kc, I'm going to take this product, square it, and that's going to be my denominator, and my numerator is going to be the aforementionedly calculated 0.0702. I get a Kc value of 6.7 times 10 to the minus 5 at 395 Kelvin. Based on our Kc value and our Kp value, these we just interchange. One is for concentration and the other one is for pressure. So if we were to have concentration of gases, this would be its equilibrium constant. If we were to have pressure of gases, this would be its equilibrium constant. The magnitude tells us that the reaction generally favors the reactant side. So an equilibrium constant that's less than 1, that equilibrium at the end of the day is going to favor reactants. That's not to say you won't get products. You will get some products. However, this reaction is generally favored to the left. You add two reactions, you actually multiply their equilibrium constants. This, remember in Hess's law, as a comparison, you're given delta H and delta H2. For the equilibrium constant, you're going to multiply. So the new K is going to be Kc1 times Kc2. This is in contrast with Hess's law, where the new delta H is going to be delta H1 plus delta H2. So the equilibrium constant has different rules than your thermodynamic parameters. So adding two reactions actually multiplies the equilibrium constants. If you're given enthalpies, you'll add the enthalpies. If you're given equilibrium constants, you multiply the equilibrium constants. So adding these two reactions together, you'll multiply these two and you'll get a value of 2.0 times 10 to the minus 17, a reaction that is heavily favored left equilibrium, or towards the reactant side. In Hess's law, if you multiply a reaction by 2, then the delta H also gets multiplied by 2. Now, this is a different situation with regards to equilibrium constants. Contrast that with the equilibrium constant, where you multiply a reaction, the equilibrium constant gets squared. So in this reaction, if I multiply this by 2 and get the bottom reaction of N2O4 going to 2NO2, the equilibrium constant, which was products over reactants, each raised to their stoichiometric coefficient, I square that and I now get a new equilibrium constant which is squared. When you multiply a reaction by a stoichiometric coefficient, you actually square the equilibrium constant. This is in contrast to Hess's law. When you multiply a reaction by a stoichiometric constant or coefficient, you multiply the corresponding delta H value. Some differences in thermodynamics versus the equilibriums. Likewise, if you divide a reaction by 2, you will have to take the square root. If you divide a reaction by 3, you take the cube root of your equilibrium constant. Here, if you divide a reaction by 2, you take your corresponding delta H and divide it by 2. So note the differences. 3 of equilibrium constants, if you flip a reaction, you actually have to take the reciprocal of the corresponding equilibrium constant. So this is in stark contrast to if you flip a reaction, Hess's law, if you flip a reaction, that means the new reaction flipped in sign. What was, thermodynamically speaking, an endothermic reaction becomes exothermic if you switch the products and reactants. Here, if you switch the products and reactants, you take the reciprocal of the corresponding equilibrium constant. So N2O4 in an equilibrium with NO2 gas, 2 moles of NO2 gas. Here is the equilibrium constant according to the law of mass action. This is the at 25 degrees. This is what the reactants and products will settle at, and they have to equal to 4.62 times 10 to the minus 3. If you want to do the opposite reaction and go 2NO2 to N2O4, you flip the equilibrium constant, and quotient deals with non-equilibrium values. So what is the formula for the reaction quotient? All right, let's go back to our equilibrium expression. Is our equilibrium expression by the law of mass action, concentration of products to their stoichiometric power times the concentration of, divided by the concentration of reactants, each raised to its stoichiometric coefficient. The reaction quotient is the exact same thing. Difference between Keq and Qc, well, if they are equal to one another, automatically know then these concentrations you're given are the equilibrium concentrations. That is, C and D and A and B are the reaction's final equilibrium concentrations. That's where they will settle at. But if there's an inequality, that's when you're going to have to realize that the reaction is going to shift either to the left or to the right of the equilibrium. So that's where alligator clause comes in. So alligator clause only works if you put Q first compared to K. C, K, P, K equilibrium, whatever the subscript of K is. You have to put Q first. So when you Q first, if greater than K, the Gator clause point to the left, the equilibrium favors the reactant side. Q first again to K. Concentrations of Q, the non-equilibrium concentrations, quotient, are less than K, then where do the Gator clause point? The Gator clause point towards the product side, and the reaction favors the product side. Doing when you calculate the reaction quotient, you're given non-equilibrium values, or you're being asked in the question, are these the equilibrium concentrations? Well, you're going to calculate using the exact same formula as the equilibrium constant. If they're equal, you're good as gold. You know you have equilibrium concentrations. The reaction has settled to the equilibrium concentration of reactants and products. But if there's an inequality, use the alligator jaws relationship. But in order for alligator jaws or alligator clause to actually work, the comparison has to have Q first. Q greater than K, the jaws point to the left, the reactant side. Q less than K. When you calculate these, the jaws favor the right-hand side and they favor the product side. Problem that involves the reaction quotient. So here we're given an equilibrium constant. Temperature, remember you quote an equilibrium constant at a specific temperature, and you're being asked to determine in which direction will the system proceed towards equilibrium. Direction will the reaction proceed towards equilibrium? Let's go ahead, calculate a reaction quotient and compare it to the equilibrium constant at this temperature. So we're given concentrations here. That is the equilibrium constant. We know that it's 6.5 times 10 to the fourth, and it has to equal to this expression given. These values of reactants and products. So let's go ahead and just calculate the concentration. The concentration of NO is, in this gas, is 0.020 moles by 2 liters, 0.010 molar. Of NO, 7 moles, 2 liters, 0.35 molar. Concentration of Cl2, 0.0083 moles, and that's also in 2 liters, 0.00415 molar. Again, these concentrations and compared to Kc, NaCl squared divided by NO squared L2, this Qc, same equation, except we're testing to see if these are equilibrium concentrations or not. NOCl is going to be 3.35. So remember, these Ks don't have units, so think about putting units here, divided by 0.010 squared times Cl2, which is 0.00415. Those values in my calculator. Value of 2.70 times fourth as my coefficient at 35 degrees C. Let's compare Kc, the actual equilibrium constant, with these equilibrium concentrations that get settled, versus the Qc, if these concentrations are at equilibrium or not. So alligator clause requires us to put Q first. So I'm going to put 2.70 times 10 to the fourth, Q first, Qc because of its concentrations. And then I'm going to put the actual Kc, 6.50 times 10 to the fourth. That Kc is going to be greater than Qc. And this reaction, according to alligator jaws, points towards the product side. So this reaction is in a non-equilibrium state. So the first thing is that these are non-equilibrium concentrations. Where will this reaction go so that it attains equilibrium? It's going to go favor the product side and settle to a concentration of this, this, and this that will equal the equilibrium constant. In order for that to do that, the reaction is going to favor the product side.